Velan is a global manufacturer of industrial valves with over 1,800 employees and 13 manufacturing plants located in 9 countries around the world. The Velan Universal Steam Trap was introduced for the first time in Canada and the United States in January of 1950. In those days, the predominant steam trap technologies in use were cumbersome, inefficient, and required frequent maintenance. Founder and CEO Mr. A.K. Velan set out to design a steam trap that was suitable for the high pressure and high temperature operating conditions that naval vessels and thermal power plants were being designed around at the time. The operation of this new steam trap was based upon the principle of a free-floating and rotating ball valve placed on the downstream side of a stellite valve seat and being actuated by a multi-segment bimetallic element. The result was a steam trap that combines effective condensate drainage with high energy efficiency and long service life. The predominant steam trap technologies today are similar to those in use when Mr. Velan set out to change the world of steam traps in 1950. For example, the thermodynamic disc trap is the most popular design used across all industries today. First patented in 1878, the thermodynamic disc trap operates on the difference in flow velocity between a liquid and a gas. When liquid is passed through the trap, the disc is pushed out of the way of the flow path, allowing free discharge of condensate. However, when steam or air enters the trap, the velocity of the flow increases and the disc is pulled onto the seat. When the steam keeping the disc closed condenses, the disc is pushed off of the seat and the cycle repeats itself. The cycling action of the TD trap results in drainage of the condensate in the steam line. However, the violent blast discharge results in large amounts of steam being lost during each cycle, as high-velocity steam flow is necessary to end the discharge cycle and close the trap. Many manufacturers of thermodynamic traps claim that flashing condensate is responsible for ending the discharge cycle and closing the trap. However, as this flow test on boiler blowdown demonstrates, the TD trap will not close in the presence of saturated condensate. Only steam flow through the trap will end the discharge cycle and close the trap. Laboratory testing shows not only that steam loss is necessary for the TD trap to operate, but also allows one to measure the amount of steam lost during each cycle of the trap. The average steam loss required for a thermodynamic trap to function is over 0.03 of a pound of steam per cycle. At current energy costs and a cycle rate of 6 times per minute, the amount of steam required to operate a fully functional thermodynamic trap is in excess of $1,000 per year. The amount of steam loss necessary to operate a population of 1,000 thermodynamic traps is in excess of $1 million annually. The inverted bucket trap is another technology widely used today. First patented in 1911, the inverted bucket trap operates on the difference in density between steam and condensate. This trap uses a bucket, open on the bottom, to operate a lever valve and orifice located in the top of the trap. In the absence of steam, the bucket sinks to the bottom, keeping the valve in the open position and allowing for free discharge of condensate. When steam or air enters the trap, the bucket becomes buoyant and floats to the top, closing the valve. When this steam condenses, the bucket sinks to the bottom, opening the lever valve and discharging the condensate once again. During normal operation, the steam inside of the bucket is continuously lost through the air vent in the top of the bucket and discharged through the lever valve. Testing shows the steam loss through the air vent to be approximately 3 pounds of steam per hour. This steam loss occurs throughout the entire life of the trap. At current energy costs, the amount of steam lost due to the operation of the air vent is over $250 per trap annually. In a plant with a population of 1,000 inverted bucket traps, the amount of energy lost due to the operation of the air vent is over $250,000 annually. The most common cause of failure for an inverted bucket trap is loss of water prime. As this demonstration shows, if the water prime is lost from the inside of the trap body, the high velocity flow through the trap prevents it from repriming itself. Loss of prime can be caused by exposure to superheat, improper sizing, mechanical wear, or simply too rapid a startup. The Velan steam trap offers an efficient alternative to conventional steam trap designs. Operating on a thermostatic principle, the Velan steam trap requires no more energy to function than is present in the condensate that collects at the drain point. The Velan steam trap uses a cantilevered bimetal stack to actuate the ball valve. There are two main advantages to the cantilevered stack. First of all, the stack can be segmented to produce closing forces which closely parallel the saturated steam curve throughout the operating range. Secondly, in combination with a spherical ball valve, the Velan trap produces a two-stage discharge. First, cracking open as temperatures drop below saturation, and then opening fully to discharge all condensate in the line ahead of the trap. To better understand this internal operation, we've constructed a test apparatus to demonstrate the internal workings of the trap. The test rig consists of a steam supply with a constant, low-volume condensate flow to the trap. The piping arrangement includes isolation valves, blowdown valves, and a liquid level gauge for visual detection of condensate. A number of instruments are installed in the pipeline which provide data to a digital recorder. The recorder monitors pressure and temperature variables at various distances from the steam trap. Pen 1 records temperature at the inlet of the trap, approximately 1 inch prior to the upstream piping connection. Pen 2 records the temperature 12 inches upstream of the trap. Pen 3 records the actual steam temperature. Pen 4 records the steam pressure. Finally, Pen 5 records the temperature inside of the steam trap. Longevity of the Velan steam trap has been widely known to major steam users for the past 60 years. Since 1950, Velan has been a pioneer in the use of cobalt-based alloys in critical components of valves and steam traps. Stellite 6 is welded into the seat facings of all steam traps manufactured by Velan. The resistance of Stellite 6 to erosion and wire drawing is over 3 times that of induction-hardened stainless steel. The result is a steam trap that routinely lasts up to 3 times longer than conventional designs under the same service conditions. Velan is currently the only manufacturer globally to use stellite as a standard material in the construction of a steam trap, and the value is well proven. Another design feature contributing to the longevity of the Velan steam trap is a modulated discharge characteristic. Under light load conditions, the discharge of the Velan steam trap will match the rate of condensate formation and collection in the line. The result is a low-velocity discharge of condensate and flash steam, which produces less mechanical wear than rival designs operating with violent blast-on, blast-off discharge patterns. An added benefit of the modulated design of the Velan steam trap is an improvement in plant safety conditions, especially in facilities where steam traps discharge to the atmosphere. The thermostatic operation of the Velan steam trap brings a number of advantages to plant personnel. Chief among these is a complete resistance to plugging and freezing. The location of the ball valve on the downstream side of the orifice has 2 major advantages. First of all, when condensate temperatures at the trap drop below saturated steam temperature, the bimetals relax and the valve is forced open by the line pressure. This ensures that the failure mode of the Velan steam trap is always in the open position, preventing freezing, waterlogging, and damage to piping and process equipment. Secondly, the downstream valve design prevents clogging of the orifice due to copper oxides or iron oxides present in the condensate. Most conventional steam trap designs locate the valve on the inlet side of the orifice. This is true for inverted bucket, thermostatic capsule, thermodynamic, and float-style steam traps. When copper oxides are present in the condensate, they build a deposit at the point in the system where the condensate flashes to steam due to pressure drop. In the case of conventional upstream valve designs, this flashing occurs inside of the trap orifice, eventually restricting and blocking condensate flow and resulting in the freezing or plugging of the equipment being drained. The Velan steam trap, with a downstream valve design, produces condensate flashing after it has passed through the orifice, leaving any hard mineral deposits on the outside of the ball valve and not inside of the orifice. Our field experience over 6 decades demonstrates that facilities that experience a high incidence of steam trap plugging due to copper oxides can reduce or eliminate this problem by changing to the Velan design. Another major advantage of the high energy efficiency of the Velan steam trap is the reduction of back pressure in closed condensate return systems. Large amounts of live steam lost to condensate return systems can cause excessive back pressure, which affects all steam traps connected to the system. By eliminating live steam loss, the Velan steam trap can reduce overall condensate return system back pressure and improve the operation of all steam traps in the system. Many steam traps manufactured today can only be installed in a single orientation. This is true for inverted bucket and float-style steam traps. The Velan steam trap will operate efficiently in any position, whether that be horizontal, vertically up, or vertically down. This makes it much easier to specify and procure steam traps without regard to final field piping configuration. The ability of the Velan steam trap to operate over a wide range of system pressures and capacity requirements make it ideal for plant standardization. The Velan multi-segmented bimetallic element, first patented in 1950, is still unique in the market today. The use of multiple segments of bimetal plates within the same element allows for operation close to the saturated steam curve. This allows the Velan steam trap to operate from atmospheric pressure all the way up to its maximum for each model without loss of condensate discharge efficiency. Conventional opposed stack bimetallic designs do not operate close to the steam curve. This results in high subcooling levels at intermediate operating pressures, making them unsuitable for use on saturated steam lines. Velan steam traps will operate at any load point within their capacity range and are designed to handle large startup or process load requirements, as well as operate efficiently in superheated conditions where there is no condensate present. These features combine to reduce the overall number of steam trap models in your plant and the amount of spare parts in your warehouse. Standardization of steam traps plant-wide is easy with Velan. Velan steam traps are manufactured for ease of maintenance and repair. Our forged steel steam traps are designed with all operating parts contained in a cage unit to minimize downtime and increase the reliability of field repairs. Simply remove the cover bolts and 2 fixing screws, and the cage unit can be replaced with a new one. Velan cage units come complete with new bimetals, valve assembly, and stellite seat. All calibration and testing has been conducted at the factory to ensure successful return to operation. Velan steam traps are also manufactured in the popular 2-bolt flange or universal connector body style. To renew the trap, simply remove the bolts holding the operating part to the pipeline connector and replace with a new unit. Velan universal connector traps are interchangeable with all other brands of pipeline connectors. This allows for easy replacement of conventional steam traps with the high-efficiency Velan steam trap. The Velan Model VTCS trap connector station represents an advance in pipeline connector technology. The advent of the 2-bolt swivel connector in the 1980s has led to major reductions in steam trap maintenance labor costs for facilities using this technology. Velan has drawn on its extensive valve design and manufacturing experience to develop the VTCS as a unit fully compliant with all relevant ASME valve standards. Built on a single-piece casting and incorporating API 602 forged steel globe valves into the design, the VTCS allows for isolation and depressurization of the steam trap for rapid maintenance. The VTCS also incorporates a strainer blowdown valve and a test valve for cleaning of debris and easy visual testing of the steam trap. All valve seats and discs are Stellite number 6 in compliance with API trim number 5 standards. Fully compliant with the ASME B16.34 standard, the VTCS is rated and tested to ASME Class 600. Velan also combines its trap connector stations with its forged steel valve products in fabricated manifolds to simplify the design and procurement process while increasing reliability over field fabricated units. Velan steam traps are manufactured in compliance with all major international quality standards using the most durable materials available today. A dedication to continuous product improvement and on-time delivery make Velan a worldwide leader in the design and manufacture of steam traps. For over 60 years, Velan has been the steam trap of choice when durability, rugged construction, energy efficiency, and critical drainage requirements are needed.